Hi, we're now going to talk about range queries, and then we're going to show some applications of range queries. Now, in a range query, you're trying to find out the sum or some combination of all of the items in a certain range. Now, this is one-dimensional range query we're talking about. Now, we could also have two-dimensional, where we have a whole bunch of items on a plane, and we want to return the sum of all the ones in a certain area. However, we won't talk about that now. Here we're only doing one-dimensional range queries. We're given an array of items, whatever items there might be, and a query to that structure is to ask what the sum of all the items between I and j is for an arbitrary I and j. Now, instead of using the plus sign, I'm using the sharp symbol because it might not be plus. The sharp could stand for addition. It could also stand for multiplication, or the maximum of the elements, or the minimum of the elements, or the leftmost element, or the rightmost element, and we'll give an application where it's something else. This application is to fast addition logarithmic circuits for adding large integers. And there we'll use something that's none of these, but it still works. Now, this particular query, this operator sharp, has to satisfy the associative law. So a plus b, or rather x plus y plus z, has to be the same no matter where I put the parentheses. So we, of course, will not use parentheses since they don't matter. But it does not have to be commutative. So x plus y does not have to equal y plus x. Now you notice that these first four operators here are commutative. This one is not. This one also is not, because x sharp y is x. Y sharp x is y. And the one that we're going to use for fast addition is also not commutative. And so we have to get used to that concept. All right, now what is the setup? The setup is that there is going to be a data structure representing all these items. And the data structure will not just be an array, but it will be some structure where we query the structure. So think of this as some sort of struct or something like that. And we put it, if we have an operator called query, so I should really write query here. Well, I'll just write Q. Query ij, and then something happens inside here, and out comes xi, the sum. I'll call it sum, even though it may not be addition. And that will be what it returns. Now, we want it to be efficient. Of course, we could just have this array. We could go in and compute the sum. And that turns out, if we're going to do a lot of queries, it's not efficient. In this theory, we're assuming that the array of x's doesn't change very often. So we'll assume it never changes. And what we have to do is first build the data structure. And that, of course, takes time. And we want to know how much space, memory space, the data structure occupies. And then we also have to know how long it takes to compute the answer to a query, how much time it takes, and how much space it uses. Now, I'm going to show you a method for doing that. First of all, a very simple idea is to have the array be the entire data structure, and the query would simply go in, pick these items out, and combine them. Now, that could take a lot of time because there could be a lot of items here. So that we would say would take O of n time. we can do a lot better than that. All right, in range queries, for example, we've already discussed that. But if one way to create the data structure is to store the value of every range query. And one other way is to store none of them, only store the array. Now, if we store the original array, that takes only O of n space. But in order to do the query, you have to add them all up in the range, which takes O of n time. But if you have parallel processors, then you can do that addition in parallel in O of log n time. Now, on the other extreme, you could simply store all query values. And if you do that, that takes O of n squared storage, because there are O of n squared possible queries. But it takes only one step to find the value query. You simply have to go into the storage and retrieve one value. Now, if you have parallel processors, that doesn't increase the speed of querying at all, although it would increase the speed of computing the data structure. Now, the most important data structure that we're going to talk about is the one that we can use for doing fast addition. And that's where we store values which are blocks of size a power of 2. It turns out that the space requirement is O of n, although it's actually twice as big as this space. The query time is O of log n, and if we have parallel processing, we can complete a query in O of log n time, which sounds interesting. Now, I'm mentioning two other structures here. These structures take more space, n log n, and the second one takes n log star n. And you realize that log star n is really very small compared to n. So n log star n is actually, from a practical point of view, only a little more than O of n. And if you do it this way, it takes only O of 1 time to evaluate a query, even whether you have even one processor or parallel processes. These data structures are much more complicated to understand than this one, though. So we might not do them. All right, now I'll explain the query structure for the blocks of size 2 to the k method. Well, what we're going to do is to store all the queries for query ij, but only for restricted values of I and j. I has to be of the form of power of 2 times an integer plus 1, and j has to be a power of a multiple of the same power of 2. And of course, a has to be less than b, because j has to be greater than or equal to I. Now, here, that means the range of a's and b's, a has to be at least 1, b has to be no more than n over 2 to the k. Now, how do you know that? Well, if b is larger than that, then j is larger than n, which is out of range. So how many pairs of a's and b's are there that satisfy these conditions in that range? And the answer is n over 2 to the k. That's how many there are. So this thing takes O of n storage. It takes n storage to hold all the blocks of size 1, approximately n over 2 storage to hold all the blocks of size 2. Now remember, when we're storing a block of size 2, we're storing 3, 4, but we're not storing 2, 3, because 2, 3 does not satisfy the conditions here for k equals 1. Now, it takes n over 4 space to store the queries of size 4, because we're not storing all queries of size 4, only those that end with a multiple of 2 to the 4. Now, how much time does it take to build this data structure? Well, there are O of n things in there, so it takes O of n time to build it. But if you use parallel processors, you can build the whole thing in of log n time by doing things at once. You do all blocks of size 1 all at the same time. Then you do all blocks of size 2 simultaneously. Then all blocks of size 4, then size 8, and so forth. So after log n levels, you're done building the structure. Now here's an example to show you. Here are 2 blocks of size each 4, 9 to 12 and 13 to 16. Remember, the blocks of size 4 are only stored if the second number is a multiple of 4. Likewise, blocks of size 8, such as this one, are only computed if the second number, j, is a multiple of 8. And so, when I take these values and add them, or whatever this operator is, could be multiply or something else, I get a block of the value for the block of size 8. And since the 8s depend on the 4s and the 4s depend on the 2s, I can do them in that order. First the 1s, then the 2s, 4s, 8s, 16s, and so forth. And after log n steps, I'm done creating these blocks. We're now going to look at the problem of adding large numbers written in binary. So we try to imagine we have an n-bit register with zeros and ones, and each register has zeros and ones representing an integer. And we would like to add 2 of these integers quickly. Now, of course, the standard grade school method is to use what's called a ripple adder. And here is the result here. You add these 2, you get a 1, add these 2, get a 0. These 2, you get 0, carry the 1, and so forth. Now, the way it works is this particular string I'll call save. And what this is the mod 2 sum of these. Like 2 zeros give you 0, 2 ones give you 0, 1 and a 0 gives you 1. So it's the sum of the 2 digits mod 2. And that operation is sometimes called plus with a circle around it, or exclusive or. It's another use for it if you think of 1 as being true and 0 as being false. Here's the actual sum written in binary after we finish the job. But what I'm going to show you here now is a way of verifying. Now, this ripple adder takes off in time. But what if we had multiple processors? We would like to be able to find the sum in less than n time, somehow making use of multiple processors. Now we'll start by doing a verification. Now, verification might not have a practical purpose, but let me show you briefly how we can use parallel processors and verify that these values, that this is the correct sum in only O of 1 time using n processors. So it means constant time, 1 step, well not 1 step, 2, 3, 4 steps, but some constant. And if we can verify in constant time, that gives us a clue that we might be able to add the numbers in way less than O of n time. So let's go through that verification. What I'll do here is the save is obtained by doing the symmetric product of the bits here, where there's no carry. And then the carry is obtained. Remember, we're verifying this result, so we have this result already. The carry is obtained by taking save and doing the symmetric difference of the actual sum and the save, these two, to get what will now actually be the carry bits. So for each place we have a carry bit coming from the right side, and that's this red number. Now, what do we do next? Let's take these three values here. The two X and Y values and the same bit in the carry bit, and then count the number of bits and add it and write those as 0, 1, 2, or 3, which is a peculiar notation you might think, but it works. And now we will verify that we have the right result. And the way we verify that is we look at each bit here, 0 or 1, and look at the sum, the ripple sum, to the right and one step to the right below it, and check to see that if we have a 0 or a 1 here, we have a 0 in the red number. If we have a 2 or a 3 there, we have a 1 in the red number. And if that's true, then the sum that we have here is correct. Now, let's look over here at how we would actually take a sum. So I'm using, like my computer here has only an 8-bit register, so I won't get carried away. And if I use a ripple adder, of course I can do that, but I don't want to do that. What I want to do is show how you could get the actual sum that you would get with an adder without using the ripple adder, and do it in a logarithmic time. So if this were very long, then the number of steps I have to use, well, I still have to use more steps, but with n processors, the total time is only log n. All right, now how do we do it? First, let's form the sum at each place, which will either be 1, 2, or 0. All right, now remember now, each processor can look at some small space, so they're independent of each other. Now what we do is we use our range query process. This will be the nth place, and we're going to do a range query from this place to here, that's this sum, from 2, 1, 1, that gives you 2. 1, 2, 1, 1 gives you 2. 1, 1 gives you 1, and just plain 1 gives you 1. But the operator I'm using is this sharp operator, which has strange rules. 0 sharp, anything is 0. 2 sharp, anything is 2. 1 sharp, anything is equal to the right side. Now we could make a little table for that, and that would be what you would do if you were writing a program. And now if I do the range queries, I would get the value. This is the query for the ith position to the last position, I being some number between 1 and 8. So we would get this 1 plus 1 is 1, 2 plus 1 plus 1 is 2, 1 plus 2 plus 1 plus 1 is 2, and so forth. And I get these values. The only ranges I'm using are ranges that go from any position to the end. And when I do that, I get a bunch of 0s, 2s, and 1s. And what we're going to do is we're going to replace each 2 by a 1 and each 1 by a 0. And that will be our carries. Except, of course, we have to peel off the leftmost one. If this leftmost bit is 1, we have an overflow situation. What is really a wrap, meaning that the answer we'll get will be mod 2 to the 8 or 2 to the n. You're familiar with that, you know. And we have to include an extra 0 on the right side because in the last place there's no carry from to the right. So therefore there's a 0 there. And now I want you to understand that there's still a string of length n here. So these are not aligned properly. This corresponds to that, this one corresponds to this, and so forth. Now, we take the symmetric difference of the 2 original strings and the carry strings, and we get the actual answer, x plus y. And well, how much time did we take? In the last video, we could see that we could do the queries, we could build the query structure, and we could find all the queries in logarithmic time using n processors. So therefore, this entire result can be obtained in logarithmic time using n processors.